So Francesca asked me to just do a quick little summary or review again, because we went quickly in the previous lecture. So I'll again just quickly go through the main ideas of the first lecture, and then we can start tackling the tutorial. Okay, and yeah, if anyone has questions, just raise your hands or send a message on that help in the Slack channel. Yeah, then we'll try to, so we can try and make this interactive. I'll try to get to all your questions, or if you're struggling somewhere, just ping on either of those channels, then we can help you out. So yeah, as a quick review, let me make this a big screen. Okay. Yeah, so it's just this Python package. May I please zoom in? Okay, I can do that. There's a... Okay, is this a bit better? Or should I zoom in more? Cool. Okay, yeah, so it's about this open source Python package SymPy, which is, like you know by now, all about symbolic computation. And this first part, let's see, we already have questions. Okay, we'll get to the symbol stuff now when I get to it on the review. And this other question. Okay, yeah, so how to open the files in Jupyter. So if you have Anaconda, you need to open it via that. So I don't have Anaconda on my system, but as I understand, you can just launch a Jupyter notebook, like Francesca showed in the beginning. And then you just need to go to where you downloaded those Jupyter notebook files and open up them through that. If that does not work, what we can also try and do actually is wonder, I know you can convert, because so is there a lot of people that's struggling to open it in Jupyter? Can you maybe give an indication of that? Then I can maybe try and get it as a Python file, and you guys can just execute it directly in Python. But that wouldn't be as great because you won't see the outputs as much. So maybe on that question, just react to Matsepu's question if you can't open it in Jupyter, then we'll try that. Otherwise, just go through through Anaconda. You should be able to open it because it comes with Jupyter installed, or you need to install Jupyter on it. Okay, so I'm going to continue then. The main idea of SymPy is it allows you to do symbolic computation instead of numerical calculations. So instead of working directly with numbers, you can work with symbols. So you can see the square root of 3 as an algebraic operation, an algebraic symbol, which if you evaluate numerically, it would be equal to this, right? But SymPy allows you to interact with it just algebraically, so not caring about the actual numerical value, because even this is just an approximation up to a certain number of decimal points, but this is the full square root of 3, right? So in a sense, this is more accurate if you just work with the algebraic symbol. Okay, and that's what the package does. It allows you to work with these symbols. And then it, like Francesca mentioned, it knows all the simplifying and factorizations of these symbols. So it knows the different representations. So like the square root of 8 is 2 times the square root of 2. And well, when you get to, it knows fractions as well. It just knows the different representations of these mathematical objects, right? Instead of just how you would normally interact with it in a with a computer, just numerically. So that's very useful for various different reasons to solve problems and things. Okay, so that's what the first part of the lecture was, just to show kind of that we're working with symbols instead of numbers, and then this basic mathematical operations is accessible through the SymPy, through the the library that you imported. So we imported as SP over here. So we have a bunch of mathematical functions and classes that we can access through that SP library. So let me see this. Just have a question to download the files before accessing them in Jupyter. And also I see there's replies on the other file. Okay, I see Benjamin is helping out with opening it up in Jupyter. And as I understand, the files are on that Canvas site. So it should all be available through that. All right, so this package gives us access to a bunch of functions and classes that allows us to work symbolically with mathematical objects, such as rationals, square roots, and addition and multiplication, and all the fun stuff. And this is an example of just some common ones. So the exponential function, or actually the exponential constant. All these constants are accessible and you can work with them. So it's just popular constants. So that's the first part. And then this eval_f function that Francesco mentioned, this is basically how you go from the symbolic to the numerical. So it's just the name of the function to evaluate whatever your symbol or expression is to a certain degree of accuracy. So this parameter just asks up to how many decimal points we want to be accurate. And then that gives it to us. So that's kind of the first part. But instead of so these are all mathematical symbols that are typically used, but you can be more general than that. You can make your own symbols. So you can make your own variables, right? And the way you do that is with this symbols function. And what this does is you give it the names of what you want your symbols to be, and then it assigns that as a variable. So this, the most simplest way of this is we have it like this, right? All this A is the variable that I can interact with in Python programmatically, and the type of it is a SymPy symbol. So it's an instance of this symbol class with a name just called A. So now I can do things like A+1, and it knows that this is a symbol, and this whole expression is that whatever value I give to that symbol, and I add 1, right? So that's the main idea there. And then you can give it a list essentially, and then you can get a list of symbols. And then this is, I guess, where we get to the Greek letters that some people had a question about. So specifically, I'm just going to read this again. So what is the issue with doing, with getting the symbols? I see someone did answer there. Just use /mu. So if you do this, does it work fine? Or is there an issue with calling these alphas and then it doesn't give it maybe as the LaTeX symbol for alpha? Otherwise, it seems like that might have got sorted out. Cool. I just want to see on the other thread here if everything is still okay. Cool. Okay. So yeah, just post another question about the Greek symbols, but I mean, it's basically you give it a string and then the name of it is the string, but then there's some ifs in the background here that runs if you're calling popular mathematical or Greek alphabetical letters, then it just prints it differently. But still, this alpha is just a variable that you use, and its name corresponds to alpha, and the way it prints it is just in this fancy way. And then what's nice about that, obviously you can set up nice computations with indices. So as Francesco just said, if you put an underscore, that's a subscript. And if you do the hat, that's a superscript, which makes it a nice way to just set up nice equations. Maybe another example that I can show you. If we have an empty expression, also I kind of just want to show what's possible with this representation. Yeah, we can create a loop that loops 5 times, and each time we want it to make a symbol, maybe. So if we want the theta, it can be like that, an underscore, and then we can actually give it an index like this. So just special format it. And then we have a temp symbol, and we can right. So you can think what this is supposed to do if it works. Let's just see. See, it's a very easy way to just get a nice printed, although you're just adding angles now, but a nice way to print, to change indices, a nice way to interact with it, because it's just a simple for loop, and you can be a bit more smart with this using this special format string. Then you can send variables in your string, so you can dynamically change the indices and values of your symbols, right? So that's pretty cool and useful, because you can create equations like this. If you maybe do another x that you want to times each theta with for some reason, it would really be, you just make another symbol and times it with x here. And then you have an interesting equation. So you can set up equations this way. And now you have this whole expression that you can try and, I guess, factor, which maybe it takes the x out. Yeah, it does that. That's cool. So you interact with it symbolically that way. And it's quite intuitive. And I think that's their whole design philosophy, is to try and stay intuitive. Yeah. Yeah. And then, you know, it starts, your building blocks is kind of these symbols. And then combining symbols with operations, you get expressions. And then I know Francesco went through all these different ways that you can create now more and more complicated expressions like these. And again, just showing that if you factor it, it knows how to factor it out. And yeah, it knows all these mathematical, like the trig laws and the different ways of representing mathematical objects. So it's really smart in that way. And also know it's not always perfect. So you can't just rely on, so for instance, this factor, the way it works in the background, it is not making assumptions, but it won't always find the simplest form of an equation. It just tries its best, and its best is really good. But don't rely on, okay, this is the exact way, maybe the simplest expression for an expression that you have. You can sometimes go a bit further or not, but its algorithm is pretty good in the way that it does it. Okay, so yeah, that's the main idea then. And then you have access to like these trig functions, or just other mathematical functions that it also knows how to interact with. Let me just see if there's any questions so far. So is everyone still following along? This makes sense. So let me see this thread. Okay, cool. That seems to be working. I see there's a, okay, cool. You guys are following along. Okay, nice. So yeah, then there was this example of the Gaussian distribution, which just was just showing the power of the SymPy function again, because in a Gaussian distribution, it's a random variable. So you have your random variable f that is the independent variable is x, and if you multiply maybe 2 random variables with each other, so if you add the other one, so f1, f2, then it's again 1 random variable. So that's just based on some statistics, and you can show mathematically, but you can show it quite easily with the SymPy expression. So that was the idea here. You have this one and you multiply another, and it takes up the form of just one again, just a bit differently. Yeah. Yeah, so that was the idea with these. I think this is all the same idea. See, there's another issue with the size here. I'll see if I can zoom in more. I'll just actually zoom in more. Maybe that's also better. Okay, yeah, we'll get to the actually executing things in just a bit. Then we can help with that. So yeah, this is now just more examples of other functions that you can use. But it's all about, I think there was a nice summary here. Yeah, I didn't see it now. But yeah, it's all about simplifying or factoring or expanding your symbols, your expressions, which consist out of symbols. Okay, yeah, and then there was just more like trig identities, just showing it knows that, and then also solving equations, which you just have to rearrange the equation so that it equals 0, and you ask it the variable you want to solve for, which is pretty cool and useful. And this just shows you that it gives you, if there's, 2 roots, then it gives you both roots to the equation and stuff like that. And so this part, I'm just gonna, so those are all the main ideas, which I think is good enough for us to jump into the tutorial. So this last part, I'll just review pretty quickly, and then we can jump into that. The other useful part here is just sums and products. So the typical summation, finite sum that you can do just has this kind of setup where you give, again, the symbol that you created, and define the range. So if I change this to a 0, that's just going to change the expression. Oh, it doesn't change the expression because we're just adding 0, so it doesn't change. But if I do -1, I wonder what that is. Okay, then it just adds the -1 in the end. So that's also pretty smart of it. But yeah, this is the simplified expression of this just summation of the first n integers, right? And yeah, so, and then if you can also do an infinite sum with that infinite constant that's accessible through, well, it's not a constant, but it's a constant in terms of programming for the SymPy. And then, yeah, this summation is, I think 2, yeah, 2. So it's just showing how to call that. Okay, so that's, there's these extra functions like summation and product and solve, and maybe these as well. These kind of things, I mean, you'll, as you start trying to solve problems that's relevant to you, you'll start to find out which of these functions is most relevant to you, right? So based on that, you'll get used to it. And the typical way that what we all do is just we try and find out how do you expand in SymPy, and then it just takes you to the documentation, and then you'll find the name of the function. The documentation is pretty good, so that's not too bad. Okay, so maybe now we can jump into the tutorial. So let's see. I'm sure, so this question asking if we can use Fourier series or any sequence to have their limit also. Yes, I think so. I wonder if it can like actually calculate limits. So you can definitely represent a limit, and maybe it would also try to calculate it for you. I'm not exactly sure on that, but there's definitely a lot you can do with limits. I mean, it knows derivatives, so it should know limits as well, right? Okay. Given a function, how can we compute the image of a fixed point? So this is just another question on the Slack. I'm not sure what you mean by that. Do you mean by image the, like, what's in the codomain? Like is that the inverse of a function? Sorry, maybe you can expand on that question. I'm not sure exactly what that means. Oh, you want to evaluate the function at a point? Yeah, you can do that. Okay, so I know of one way to do that, which I guess I can share that. So let's create an expression. Or so first, just let's create our function. Maybe we just have a function of x, right? And we say, let's just give the expression of the function, and maybe it's just x squared plus 2x plus 100. Okay, and then the way that you convert that into a function callable that evaluates the number, and it's callable by what you call it, by Python. I just need to get a piece of code here. So there's this function in SymPy called Lambdafy. So I don't know if you guys are familiar with Lambda functions, but on a high level, a Lambda function is just a way to create a function in Python in one line, right? So there's I need to remove a y. Yeah, 2xy, thank you. That would have not worked. Cool, so that's just our expression. And then, let me show it like this way. There's this Lambdafy function. So it turns this expression into like a callable function, the same way an actual callable function that, usually you define like my function like this. It turns it into this kind of function with whatever parameters, okay? So the parameters to this Lambdafy function is you give it the expression and you give it the symbols in the expression that you want to replace with a numerical value. So we only have one symbol, x. So this is the only thing we're going to give that. So now we have our function, and I need a times there. It's fine. Cool. And now you can just do f of 2, which should be 2 squared plus 2x plus 100, which is 108. And f of maybe 2.6 should work as x. So that's how you do that part. And you can do pretty cool stuff. It can still, maybe I add another symbol here, right? So we have a symbol x and y. So now we have our two symbols and we add a y. So now this expects a list. So we just give it the two symbols x, y, right? And now we have our function, but I need to give it two values, one for x and one for y. So let's do our this was 108 plus the y should be 109 or something like that, right? So we have our 109, but you could still have just asked it, just give it me, keep this y a symbol, right? So part of it's you don't know the values of the other symbol that you might want to use. So I'm only going to give numerical values for x and then give me the expression. So then I think it should give you, yeah, it gives it for you in terms of y. And now this f of 2 is an expression, right? So you can, if you wanted to be fancy, turn this into your g, which would be for y now, right? And then you can give g just the value of y, which would be that 108 plus 3, which is 111. But this is just complicating it, but you get the idea, right? So it's all this Lambdafy function, which works pretty well. If you have a very complicated expression, which you can also do, and you don't want to type out all of the symbols that the expression is using, an expression has this property called free symbols, yes, which gives you which returns a set of all the symbols it uses. And remember, Lambdafy wants a list. So if you turn this into a list and you give it to Lambdafy, then you don't even need to type out it then knows it's going to be x and y. So the reason you need to turn it into a list, because I'm assuming my first parameter is x and my second one is y, and a list is ordered where a set isn't ordered. So you're just, you have to define your order, which would now just be the order in which we initially created it. Okay, so that, yeah, I think that answers that question. And let's see, how do I get the Greek letters as variable names in cell 14? Cell 14, does it have numbers here? So is it this one? I know this is kind of strange. Maybe is this what they mean if you do it like that? Yeah, that doesn't work. The only way I can think about getting, so I don't know, but the only way that I can think about doing it is if you maybe do A equals mu, right? If you have your symbol and it renders as mu, and if I copy mu directly from the cell, it's probably going to remember it as a mu, and then you can maybe use that as a variable for Python. But I probably, yeah, so you can do it that way. I don't know of another way, really. But usually when you're programming things, I think it's fine to just keep with the normal, use variable names only as things that's directly available on your keyboard. Maybe there is a shortcut for it, but you might run into issues if you change different like IDEs. So maybe Jupyter, well, I guess Python can interpret it. So I don't know. Maybe just I'd stay with just letters for variable names is simpler. I think for other people as well, if they read the code. So it depends. But this is one way that you can do it. You can copy and paste it. Yeah. Yeah, and then I guess the other way is to do it in the markdown and do the \mu. So let's see, there's an error here. Okay, so your error is saying SP is not defined. You need to import SymPy as SP, right? So above in the cells, I had there's an import SymPy as SP. So you'll need that for this cell to be able to run on its own. Cool. And then another question, what about plotting the graph of a function? Yeah, so that I'm not sure about in SymPy. I'm not sure if you can give it, well, you should probably be able to give it an expression and then it tries to plot it for you over X. But as Francesco also mentioned, you can do that the normal way in matplotlib, which I'm not sure if you guys learned that, but there's a lot of resources online about how to do that. So you can either use matplotlib or you use NumPy to create a range of X values and then plot it in matplotlib. And as Andrew says, there is a way to do it in SymPy. I'm just not aware, so I haven't done that yet. But yeah, I'm sure there's a way. Okay, let's jump to the tutorial, which doesn't have too many exercises. So I know in the notebooks that you guys download, the answers are there. So I'll trust that you don't look at the answers directly and maybe just try the exercise here. Maybe create a new Jupyter notebook and run these. Actually, you just need this cell and then try and do this exercise, which is just show that this expression is the same as this expression, I guess, using SymPy. Yeah, and then I'll leave this on the screen, and then if anyone has questions, just ask in the chat, and then we'll try to help out. When enough people have replied and see if it works, then we'll go to the next exercise. So try and not look at exactly how to do it, because then you might not learn as much. Just looking at this and a whole empty Jupyter notebook, maybe try and show this. Cool. While you guys try the exercise, I'm gonna So I'm gonna try do the plotting. Okay. Okay, so if you guys want to look, the plotting is pretty straightforward. I just, Andrew provided a link, and you can really just create your symbol and create an expression or a relation, and then just give that expression to this plot function, which you import from SymPy.plotting. And yeah, you just show the plot just like this. And does it use the same? So you can do, if you wanted to do x squared, it would have been like that. And yeah, you get the idea. So it's pretty straightforward. Okay, were you guys able to do this, or do you need more time? Can you give me an indication in the Slack channel? I should go on, or if there's anyone struggling. Okay, more time's fine. Cool, cool, cool. Yeah, no, we'll give more time. No worries.